All right, so we're going to take a look at each of these separately, and hopefully you took notes on the last slide so you can kind of compare your notes with each of these. But let's take a look at the function first, and then we'll compare that with the graph of the derivative. So we said that the function was decreasing from negative infinity to 0, increasing from 0 to where are you at? 0 to 4, right? Yeah, 0 to 4. And then decreasing from 4 to positive infinity, which is exactly what's happening here. We can move this along. Decreasing from 4 to positive infinity, okay? And you can graph this on Desmos and C as well, but that's what we've got going on here. It looks like we have a horizontal tangents, sorry, we've got horizontal tangents at 0 and at 4, which coincides with, that's where we found f prime of x to be equal to 0. All right, that's where we found f prime of x to be equal to 0. We see that we are concave up from negative infinity to about 2, which is hard to really see on this graph. So we said it was 216. So that point, we're concave up from negative infinity to 2, and then concave down from 2 to infinity. So right here we have a point of inflection, and that's where we switch concavities. So let's take a look at the graph of the derivative in comparison to what we were just talking about. So here's the graph of the derivative. Notice that the first derivative is equal to 0, okay, horizontal tangents at 0 and 4. So here is your first derivative equal to 0 at 0 and 4, because this is a graph of f prime of x. And f prime of x is 0, y is equal to 0 right here and right here, which signifies horizontal tangents on your function. Horizontal tangent, horizontal tangent, horizontal tangent, horizontal tangent. Okay, because that's f prime of x is 0, y is equal to 0 there. Notice how before that, right here, our f prime of x's, our y's there, are smaller than 0, and that should be where our function is decreasing from negative infinity up to 0, which it is. It's coming down from negative infinity to 0. And then all our y values up here are positive, and that's going from 0 to 4. So that should be our function is increasing from 0 to 4 because all our y values here are positive. So here's 0, and here's x equals 4. So our function is certainly going up. And then after 4, my y values are all negative. So my function should be decreasing after 4. So here's 4, and my function is decreasing. So that's how we are analyzing the functions. When you're reading this and talking about him, you're reading it completely different than when you read this. Here we're looking for positives and negatives to kind of see the behavior, the sketch of the function. So we're analyzing the derivative to sketch the function. Now let's take a look at the second derivative. Remember, the second derivative talks to us about concavity. And it looks like our second derivative changes signs at 2, which we expected. Our second derivative is, sorry, that should be an x. Our second derivative is greater than 0 or positive from negative infinity to 2. And right here, our second derivative is negative from 2 to infinity. So what did that mean for the function? That meant concave up from negative infinity to 2. And right here, that means concave down. And since we changed signs, then that's a point of inflection. At 2, not at 2, 0, because 2, 0 is on f double prime of x, on 216. And that's true, we are concave up from negative infinity to 2, matching right here. And we are concave down from 2 to positive infinity. So hopefully you read these side by side. And that's basically what the reading is going to go through. So I'm going to go ahead and quickly just discuss the first and second derivative test, which we've kind of already done, and then give you your assignment. On page 111 in the manual, you find the first derivative test. It is an important theorem, and it's basically kind of attaching everything we've just talked about to minimums and maximums. So let's C be a critical value of a continuous function on an interval containing C. If f is differentiable on that interval, so it has to be a differentiable function, or this doesn't work because we're running a first derivative test, so the function needs to be differentiable. And C is one of those critical values. We called them critical points. So C is a critical value, which means either f prime of x is 0 or f prime of x was undefined. Which we'll do one of these. I'll do one where f prime of x is undefined before I let you go. All right. So if f prime of x changes from negative to positive at C, then f has a relative minimum at that point, at C, f of C. Relative minimum is like a bottom of a hill. If f prime of x changes from positive to negative, which means the function changes from increasing to decreasing, then there's a relative maximum at C, f of C. And if f prime of x is both positive on both sides or both negative on both sides, then it's neither a relative max or min, kind of like this right here. This point is a critical point. It was probably f prime of x was undefined there. And when you checked the left and the right on the derivative, the signs didn't change. You had positive and you had positive. So this is a function. Notice how the slope of the tangent is positive, slope of the tangent positive. As opposed to this function, these are all graphs of f of x, by the way, not graphs of the derivative. These are all graphs of f of x. Notice the slopes here, the first derivative positive, first derivative negative, maximum. First derivative negative, first derivative positive, minimum. Okay, so if we take a look at the example we did before with x squared, f prime of x, f of x equals x squared, and then f prime of x was equal to 2x, we see here that the point 0, 0 is a relative minimum. Okay, and how did that jive with our sign chart? Well, we set 2x equal to 0. We found a critical point at x equals 0. Okay, that's supposed to be a 0. So this guy right here, he's either going to be a relative min, or he's going to be a relative max, or he's going to be neither. Well, when we plugged in values below 0, we got negatives in our f prime. When we plugged in values above 0, we got positives in our f prime. And since f prime of x changed from negative to positive at x equals 0, that means we have a relative minimum at the point 0, f of 0, also known as 0, 0 in this case. And if it would have gone the other way around, then we have a relative maximum. But that's not what happened. Okay? So let's take a look back at the big function we had done before. Here's the one we had worked on before. And I know we got a lot of writing on here, but here was our derivative. And we saw here that our derivative changed signs at 0 and changed signs at 4, and we talked about increasing and decreasing. Okay, so where are the relative minimums and maximums? Do we have any? Well, it looks like we have a relative, we're going from decreasing to increasing at 0. So we have a relative minimum at 0, comma f of 0, which we'll figure out what that is in a second. Oh, it's 0, because here's the function. So we have a relative minimum at 0, 0, and we have a relative maximum at 4, comma, and I just remember from looking at the graph, at 4, comma, 32, which is f of 4. And again, right here, our graph is going up and then down. And I've seen students kind of draw these ups, downs to help them visualize it. And we saw that when we looked at the function, when we looked at the graph, we saw the lowest point and the highest point. And we're going to talk about absolute maximums and absolute minimums, but for right now, we're talking just relative maximums and relative minimums. The second derivative test, which you can find on page 114, is another test we can do to find relative maxes and mins. So we already talked about the first derivative test to find maxes and mins. We can also use a second derivative test. I'll be very honest with you. I mean, you should know both of them. I always tend to use this one. I mean, it's obviously very helpful to use the second derivative, or know the second derivative test as well, but I usually use this one to test for maxes and mins. Second derivative test says, you know, obviously the function has to have a second derivative that exists, or this won't work. If the second derivative is positive, then f has a relative, or second derivative at c is positive, then f has a relative minimum at c, f of c. If the second derivative at c is negative, then f has a relative maximum at c, f of c. And if the second derivative of c is equal to 0, then the test fails, and you must use the first derivative test to certain relative extremes. Okay, I mean, I've usually used the first derivative test, but if we want to find use the second derivative test to find extrema, we can do one of those. Our first derivative here is 30x to the fourth minus 30x to the fifth, and our second derivative is 120 x to the third minus 150 x to the fourth. That is a lot of x's. And let's say I want to check to see if there is a relative max or min at x equals 1. I just arbitrarily picked x equals 1, okay? Since I have the second derivative here, I can go ahead and plug 1 into the second derivative, and I find that that's equal to, to negative 30, and it's negative. So since f double prime of 1 is a negative number, I have a relative, since f double prime is a negative number, I have a relative maximum. It's kind of like feels backwards. Since f double prime is negative, I have a relative maximum at 1. And if you look at the graph here, I should have just pointed with the pointer here. If you look at the graph of the function, 6x to the fifth minus 5x to the sixth, you do have a relative maximum at x equals 1. How did I pick 1? I just arbitrarily picked a number. Obviously, you don't have like a variety of numbers to pick from here, and usually if you're using the second derivative test, I mean, you can pick some. But usually we're using the first derivative test to test for relative extreme. So on this page here of the manual, which is page 115, you've got a super handy dandy table that summarizes everything we've talked about. Remember, we've also talked about critical points, which is where f prime of x is equal to 0 or undefined. We've talked about points of inflection, which is where f double prime of x is equal to 0 and it changes signs to the left and to the right of that value. Because you can have f double prime of x equals 0, and then when we do our sign chart to test what happens to the left and to the right of that value, it doesn't change signs. So that could happen. You could find a value and then it just doesn't change signs, which means it's either concave up the whole time or concave down the whole time. Okay? So I'm going to go ahead and ask you to try page 110, number 2, page 112, numbers 5 through 8, and this page, 113, nope, this is not this page, page 113, sorry, numbers 9 and 10, and page 115, number 15. Okay, so it's basically most of the example problems. And we'll check these in class on Monday, and you'll have some work time and time to Q&A on Monday. So work time on some of the homework questions and time to Q&A on Monday on these problems. Please feel free to ask me any questions as you try these on your own, and be prepared to ask questions on Monday as we take an opportunity to kind of stop, rest, and assess and see how we're doing with these. Okay, so be prepared with questions. Thanks, guys.